Well, hello and welcome back to another episode of Quantitative Bytes. It's great to see you all. I hope you're all doing well. Another week has gone past. It's hard to believe, really. It's gone incredibly quickly over the last week. Now, in the last episode, I talked about what I planned to do this week, and I said specifically that I wanted to look at writing the code to implement triangles, and that's exactly what I've been doing, and that's precisely what I want to talk about in this video today. Now, if you remember, not the last episode, the episode before, we looked at writing code to implement filled polygons so that we could draw filled polygons using our 2D primitives library. And that's all well and good. And so the obvious question is, well, if we have that code already, why don't we just use that to draw triangles? After all, a triangle is just a special case of a filled polygon. And the reason not to do that is that the filled polygon code is actually quite slow because it was written to be able to work with any possible configuration of vertices that the user might provide. It couldn't really make any specific assumptions about the shapes that we were dealing with, and therefore it was necessary to implement it in a particular way that is actually quite slow. Now, triangles are quite an interesting special case of a filled polygon. They have certain geometric characteristics, for example, the fact that they are always convex, that actually make them relatively easy to render. And because of that, there are other ways that we can go about rendering triangles specifically. Now, these ways work only for triangles. They wouldn't work for other shapes or other generically for filled polygons, but they do work for triangles. And as you will see, the code that we can implement using one variant of these techniques that I've come up with is much faster than the equivalent code that we developed in the episode on filled polygons. What I want to do before we sort of jump into the code, as always, I want to quickly just go over the geometry of the situation that we're talking about. So if we think about a triangle, we see the example here, a triangle consisting of three vertices that here we have labeled V1, V2 and V3. Now, between these three vertices, obviously to form the triangle, we draw the corresponding edges, E1, E2 and E3, as you can see here. Of course, that's naturally how we do a triangle. Now, this example we've done, this is a very simple equilateral triangle. This algorithm actually does work for any configuration of triangle, but I will leave it to you to sketch out some examples on paper and you can verify that for yourselves. Now, if we were going to use the FilledPoly algorithm to render this triangle, to fill in the triangle shape between the three vertices, what we would do is we would look at every point within the bounding box of the shape, and we consider two example points as you can see here, and then for each one of those points we would cast a line out horizontally from that point in one direction in the positive x-axis, in the positive x direction, to the very extreme edge of the bounding box. And then we simply count how many times that line intersects with edges of our shape. So we can see here the point that is inside the triangle intersects once, and the point that is outside the triangle will intersect twice. Now, the way to do that for generic polygons, then, to decide whether we're inside or outside, is to count that number of edge intersections and then see whether that number is even or if it's odd. If we cross an even number of edges, then we know we must be outside the shape. And if we cross an odd number of edges, then we know we must be inside the shape. Now, we talked about that in the episode specifically on filled polygons. I'll put a link to that up here so you can go and watch that episode if you wish. It turns out that there's quite a different way that we can go about doing triangles that is substantially faster. So if we go back to the situation that we have as shown here with the three vertices, actually what we could do is we can interpolate all of the points between each pair of vertices, as you can see here. So between V1 and V2, and between V2 and V3, and between V3 and V1. And then we can see that if we wanted to fill this triangle in, if we wanted to render a filled version of this triangle, all we really need to do is draw horizontal lines between each pair of the coordinates that we get back from that interpolation process. So we can see clearly from this diagram that for every unique value of y between the bounds of the triangle, there are two values of x. So it's then really quite easy. All we need to do is to be able to identify those pairs of points for each value of y, and then we can identify the corresponding points of x, and then we know that all we have to do is draw a horizontal line between those two x points, and that takes care of that part. And then, as you can see in the demonstration here to my if we just repeat that process for every pair of points for each value of y, then we will end up drawing the filled triangle. Now notice that in this example we don't actually need to interpolate between v1 and v2, and that's because they are already horizontal. The y value for v1 is equal to the y value of v2, and so we can just ignore it. As I said at the beginning, I'll leave it for you as an exercise if you want to sketch out some different triangular geometries and confirm that this method actually holds true for any particular example of triangle. I've just gone for a simple equilateral triangle here for ease of demonstration, but the same method applies for any shape of triangle you care to imagine. So we end up with an algorithm that looks something like this. So what we do is for every pair of vertices, so v1 and v2, or v2 and v3, or v3 and v1, we first check that the y-coordinates of those vertices are the same. So if they are, then we know the line is horizontal and we don't do anything that, so we just skip it. If the y-coordinates of the two vertices, however, are different, then we need to interpolate between those two vertices. And all we do is we do the very basic linear interpolation between those 2 points to give us every point in between the two, and we store those interpolated points into an array. And then we simply repeat that for the next pair of vertices and then for the final third pair of vertices, each time adding the new points that we've interpolated into the array that we created at the beginning. So we end up with one array that contains all of the interpolated points corresponding to the edges of our triangle. So once we've done that, we have a single array that contains all of the points corresponding to the edges of our triangle, except of course in cases where the edge was perfectly horizontal. And we can see that what we need to do then to implement our triangle drawing algorithm is to find each pair of points with equal y values from that array. Now, I have gone about doing that using a sort method. So what I decided to do was to simply sort that resulting array so that it's in ascending order of the y values. And you'll see when we come to look at the code what I mean by that, and I think it will become more clear then. But if we sort that array in such a way by y values, we will end up with something that looks like this. So we have here an array that contains points. All points have both x and y coordinates. And because we've sorted the array in ascending order of the y coordinates, we will end up with the pairs naturally will become consecutively. So we can see if we look at the first entry in this array, and we see that it has the same value as the second entry, and then the third entry has the same value as the fourth entry, the fifth entry has the same value as the sixth entry, and so on. And we can see then that's quite an easy way of then pairing these up. So then all we need to do to actually be able to render the triangle is to be able to loop through this array in steps of 2, and we know that the ith value and then the I plus 1th value of the array are the two that we need to consider, and then we just need to draw a horizontal line between the two corresponding x coordinates. And actually that's it. It's really not that complicated, and it is a whole lot more efficient than trying to do it using the FilledPoly algorithm that we talked about before, which is good. Now, this is just sort of the way that I sort of sat down and I thought about how would I go about doing this to draw triangles. I believe that there are other ways of doing it. The basic principle is the same, to identify all of the edge points using interpolation, but I think there are different ways it can be done then to decide or to find exactly which pairs to draw lines between two. And it's possible that those other ways perhaps of doing it are more efficient. So this is what I've come up with over the last week, and as we'll see when we come to look at the code and to run the code, this actually does run quite efficiently, and it's efficient enough for what I want to do. What we're certainly not trying to do is create some kind of software alternative to OpenGL or something like that. That would require something that was probably quite a lot faster than this, and clearly we're not going to compete with that kind of thing anyway. So OpenGL triangle drawing algorithms are highly optimized and designed for parallel execution and everything else, and we're not going to get anything like that kind of triangle rendering speed from an algorithm like this. However, for the use case that I have in mind, where we simply need to be able to use it to create simple two-dimensional shapes, rectangles, and that sort of thing, and I've talked before about wanting to be able to create lines of specified thickness. I want to do that using these triangles, essentially to create rectangular segments. This approach, I believe, is actually fast enough. And you know, I'm not saying this is definitely the most efficient way of doing it, but I think it's quite, in terms of the code, I think this is quite an elegant solution. And yeah, so, and as I say, it's efficient enough for the purposes that I have in mind. Okay, so without really much further ado, I think what we should do is head over to the computer and have a look at the code. And I think any questions you may have about the explanation that I've just given will hopefully be answered when we look at the actual code. Just before we do that, however, I just want to say, as always, if you've liked this video, please remember to hit that like button. And if you haven't done so already, please remember to subscribe to my channel so that you don't have to miss any future videos. I do try to produce one video every week, at least one a week. Occasionally I don't make it. It depends on, you know, the day job and everything else, anything else that's going on at the time. But I do try to make a video every week. So if you subscribe, then you can be sure you're not going to miss anything. Okay, let's go to the computer and let's have a look at the code. Okay, so here we are at the computer. Now, actually, before we just jump in and talk about the code for rendering triangles with the algorithm that we've just described, I just wanted to mention I did find that there was a bug in object.cpp, just in case anyone is following along and following my code exactly, which is fine if you want to do that, absolutely not a problem. It isn't, strictly speaking, what I recommend doing. I do rather that people would watch my videos and look at how I go about doing things and then take away from that inspiration and ideas and then go off and create your own code to implement 2D primitives library or whatever else that you want to do. However, if you are choosing to follow along, then for those people, I just wanted to say that here in the convert color function or convert color method within the object.cpp file, I realized I had made a mistake. So where the purpose of this function is to convert the specified instance of the QBColor class into a uint32 that represents the proper pixel encoding to implement that color. The mistake I had made is that I had actually specified these instead of color as m_color. So this was converting the member variable for the color that has been stored when the instance of the particular shape was created, rather than the color that's actually specified here or passed to the function, which obviously doesn't necessarily then give the right results. If you wanted to generate some kind of other color in your code for implementing a specific shape other than the main color that the user has specified for that shape, then the way it was written before, that wouldn't work. So all of these references here to color should be color from this variable here that is passed to the function, and not m_color, the member variable. It's a minor thing. It came up because while trying to debug the triangle algorithm, I wanted it to render different things in different colors, and for some reason it just wouldn't do it, and it really confused me for actually quite a long time. It just seemed to be completely ignoring why my specifications for the color, and it took me a while to find that the mistake was actually here in object.cpp. So there we go, just wanted to quickly mention that. Okay, with that out of the way, let's have a look at the code that I've written to actually implement the triangle class. So we're creating a new shape class. So of course I've gone ahead and created triangle.h and triangle.cpp accordingly. And we don't need to talk about this too much. The header file is pretty much the same as the header files we've used for the other shapes. We include the bunch of stuff that we need. We put this inside the QBLib2D namespace. We declare the class of triangle that inherits from the object, object of course being the base class that we're using. And then we just define the public function. So we have a constructor. As with all the constructors, this accepts as the first input parameter a pointer to the renderer. It then accepts three SDL point structures corresponding to the three vertices. Of course, a triangle, we know it has three vertices, so there's no need to use arrays or anything like that. We can actually just allow the user to specify them individually. And then, of course, we accept a QB instance of QBColor to the color that the user wants this triangle to be. With the destructor function as normal, we override the SDL, the getBounds function as before, we override the render function as before, we override the translate function. That's the one that we introduced in the video last week when we talked about simple animation. We don't need to talk about those. Now, private functions, we have a couple here that are quite different. So, of course, we have compute bounds and update. These are common to all of the shapes. Again, we've talked about the functionality of those. I'll mention that briefly when we come to look at the CPP file. for people who might not have seen the previous videos. We then also define a interpolate function, now the private function for this class, that accepts as input 2 points specified by x1, y1 and x2, y2, and also accepts a pointer to an instance of the SDD vector class called edge points. And finally, we have a static function here. So static being meaning that we can actually call this function without it belonging to a specific instance of the triangle class. And it's simply called point sort function. And the purpose of that will become clear when we come to look at the main code. And then finally, we have two member variables. Both are STD arrays, m_vx and m_vy. The purpose of those obviously just to store the x and y coordinates of our three vertices. Because this is a triangle, we know it has three vertices. It's only ever going to have three vertices, no more, no less. We only need to use STD array. There's no need to use STD vector for that. And that's pretty much it for the header file. That's really very simple. So let's go ahead and look at the CPP file. So here I'm looking at triangle.cpp. Of course, we hash include triangle.h, and then we use algorithm, and I've included IOStream for the moment. Really, that was more for debugging. I don't think we strictly need it anymore. It gives us access to cout, so we can write things out to the terminal, which is useful for debugging. Anyway, so as we've just seen, our constructor function accepts as input the pointer to the renderer that we just store and the color that we just store, as we can see here, and then we simply accept the three vertices as three separate SDL point structures. And all we have to do is store those points into the relevant arrays. So we just do m_vx0 is v1.x, mvx1 is v2.x, mvx2 is v3.x, and the same for y. Really very simple. And then in exactly the same kind of structure that we've done for every other shape up to now, we then call compute bounds to calculate the dimensions of the bounding box for this shape, and then we call the update method that is responsible for actually rendering the shape into the texture. I'm not going to talk about why we're doing that here. If you want to know more about what I mean by rendering into a texture, go back and look at the episode on faster circles, episode 2 of the series. I'll put a link up in the top of the window here. Okay, the destructor, we don't actually define anything in there for the moment, and then we have to override the getBounds method, but it just returns mBounds. That's very simple. Now the compute bounds function, I realized actually there's a much more efficient way of implementing this, and this is what I should do for the FilledPoly code as well. I will go back and change that, but all we need to do is really determine the minimum and maximum x and y values of the specified vertices, and then that tells us the dimensions of our bounding box. So we can use the min element function from the standard library to do that, which is very convenient. So we just do std : min element, and then we go from m_vx dot begin to m_vx dot end, and that will find the minimum element in that array between beginning and end. Now it actually returns a pointer to that rather than the element itself, so we put this star at the front to say we want the value corresponding to that pointer, not the actual pointer itself. And we subtract 1 because, as in the case of FilledPoly, we want our bounding box to be ever so slightly larger than the shape that we're actually considering. And then we do exactly the same thing there for min y, it's obvious, and max x and max y are the same. And then we simply store those into the mBounds structure. mBounds, of course, is of type SDL rect, so we simply store x, y, and width and height accordingly. Then there's the update function. That's responsible for actually doing the drawing, so I'm going to come back and talk about that in a moment. I just wanted to mention here that we have the render method. This is exactly the same as the render method or the render function, sorry, for all of the other shapes that we've done, so I'm not going to talk about that here. Translate I haven't actually implemented yet. I need to do that so we can do simple 2D animation with this class of shapes, but that's still to do. I'll do that in a moment. Now interpolate, this is the interesting function that actually interpolates between 2 points. So this is a very simple implementation actually of just classic basic linear interpolation, so I'm not going to explain it too much, but I want to explain a little bit about what we do with this array or this vector edge points that we have as input. So what we're going to do is interpolate between the point specified by x1, y1 and the point specified by x2 and y2. Now the first thing that we need to check is if these 2 points describe a horizontal line, then we're just not going to do anything. Okay, so if y1 is equal to y2, we don't do anything. So we check if y1 is not equal to y2, then we know we have to do stuff. And then we need these to be in a specific order. So what we want is we need y2 to be the larger value, but there is no guarantee about the order in which they will have been passed to this function by the user or by the calling function. So we very simply check that if y2 is less than y1, then we use the swap function from the standard library to simply swap y2 and y1 and also x2 and x1. Okay. That's fairly self-evident, I think. We then compute our x and y range. It's simply, of course, the difference between y2 and y1 and x2 and x1. Of course, we know now that y2 is going to be larger than y1. We haven't forced that for x, okay? So just because we swapped them here, there is no guarantee that x2 will be larger than x1, but that doesn't actually matter, okay? We then define the step size in the x axis, which is simply the x range divided by the y range. Very simple. And yeah, and then as a floating point, obviously, so we have to static cast these variables to float before we divide them, and of course our result is a float. And then we simply loop through each value of y and compute the corresponding value of x. So we set a count to 0, and we loop for ty from y1 to y2, and then for each value we calculate our value of tx, which we static cast. It has to be an integer, so we static cast int, and we take the round of x1 plus the step size multiplied by count. So count is simply the number of points that we've looped through. Because we're looping from y1 to y2, we need to keep a separate count variable that runs from 0 and then increments. And then every point that we get there, we get 2 points tx and ty, and we simply push those back into the edge points vector that has been passed to the function. So the point of that is that we can call interpolate 3 times for the points between the first vertex and the second vertex, and then between the second vertex and the third vertex, and then the third vertex and the first vertex, and we can pass it a reference to the same vector every time. And what that will do is simply add the newly interpolated points onto that existing array, which I think is quite a good way of doing things. And then we just have to increment count, and we then continue with that loop until we're finished. Point sort function, going to come back to that in a moment. You'll see why. So let's have a look at the update function. So this is really the function that does all the actual work. So, of course, first of all, we call the init texture function from the base class just to set up the texture that we're using. We allocate memory for a pixel buffer and clear it. We talked about that in all the previous videos, the previous shapes. So I'm not going to go into that in any great detail. Now, the first thing we need to do is normalize the input coordinate. The user specifies the coordinates of the vertices anywhere on the window, and then we calculate a bounding box around those. But we're rendering into a texture. Now, of course, the texture is mapped from 0, 0 to bounding box width and bounding box height. So it doesn't correspond necessarily to the same x and y position on the screen or in the window. So we need to, I've called it normalize. I don't know if an offset might have been better, but so basically all we're going to do is loop through each of the 3 vertices. We create 2 new arrays called normx and normy, and then so normx, each value of normx is simply equal to the corresponding value of m_vx minus mbounds.x. So I think you can probably see quite easily what that's going to do. It's going to remove the x offset so that we then map from 0 to the width and from 0 to the height. Okay, I think if you sit down and think about that with a pen and paper, that will be quite clear if it isn't already. Now we're going to use the interpolate function to interpolate between all 3 of the vertices. So first of all, we create the vector edge points that we've talked about, the instance of std vector called edge points of type SDL point. Okay, and then we call the interpolate function first with between normx 0, norm y0, and normx1 and norm y1. So that's between the first 2 vertices with a reference to edge points. And then we do that again between normx1, norm y1, and normx2, norm y2, and again a reference to edge points. And then finally, between norm x2, norm y2, and norm x0, norm y0. So that takes us back to the first point, and again, a reference to edge points. So the really important thing here is that we're using the same instance of the std vector class every time. We're simply passing the same reference. So what that means is that each time we call this interpolate function, it's going to add all the new edge points into this same array. So after we've called interpolate 3 times, we will have one vector called edge points that contains all of the x and y coordinates corresponding to all of the edge points in the triangle. Okay, and this is the interesting bit. Now, as I mentioned before in the introduction, we need to sort that, but we need to sort it in the order of the y coordinates only. Okay, so we're using the sort function from the standard library, and we're sorting from the beginning of edge points to the end of edge points, which means we sort the whole array, the whole vector. But because we want to sort by only the y coordinate, and we have, of course, each element of this array of this vector is a structure of SDL point. It has both x and y. And we want to sort only by y. We have to define a custom point sort function in order to do that, okay? And that is the function that we saw previously down here. This is the point sort function. It was declared static in the header file that we just saw, and it accepts as input 2 points called I and j, both instances of SDL point. It returns a boolean, and it simply returns I.y less than j.y. So that means it's going to only perform the sort on the y coordinate of the list of SDL point structures, rather than trying to do something involving both x and y. So I think that's a very powerful capability of the sort function from the standard library, in that we can actually specify a custom comparison operation. If you didn't do that, then sort will simply do a basic comparison between these two, which I don't really know what would happen if you were to do that, because we passed this as a vector of structures. If you pass simply a simple numerical array, then it will simply compare using, I think, the less than operator, really simple, unless you specify some kind of custom function there. So, as we saw in the introduction, after we do that, each pair of points in edge point should now have the same y value, and all we need to do is draw a horizontal line for each y value between the two corresponding x values. Okay, so first of all, we use the convertColor function from the base class to convert the color that the user specified as an instance of the QBColor class into a uint32 called pixel color. And now we're going to simply loop through every element, or every element in edge points. So we do a loop for I equals 0, I less than edge points.size at -1, because we're going to do a step size of 2, okay? And what we do is we extract the coordinates that we need. We need the value of x1, so that's simply given by edge points of I dot x. And then we need the value of x2, which is going to be edge points I plus 1 dot x. Then we only need to bother with one of the y coordinates, because we have, through this process, we've ensured that the two y coordinates will be the same. So we just extract y1 is simply edge points of I dot y. Now, we want to make sure that we draw from the minimum to the maximum value of x. So we need to swap x1 and x2 if necessary in order to ensure that. So if x2 is less than x1, then we use the swap function from the standard library simply to swap x1 and x2. And now we know that x1 is going to be smaller than x2. We do a very simple for loop to loop through for int x equals x1 to x less than or equal to x2 plus plus x. And then it's very simply a matter of modifying the relevant element in our temp pixels pixel buffer, simply given by y1 times mbounds.width plus x equals pixel color. And that actually is it. That is really everything that we do to render the shape into the texture. So or into the pixel buffer anyway. And then we use the SDL update texture method, as we've seen before with the other shapes, to modify mTexture with the value of with the data from temp pixels. And that's really it. And then we just, at the end, we destroy the pixel buffer using the delete function. And that actually is everything. So that's it. That's the basic implementation that I have come up with for fast rendering of triangles, or relatively fast rendering of triangles. I think perhaps there might be more efficient ways of doing it that don't necessarily involve using the sort, or using a kind of sort function. Now, the sort function, of course, has a complexity of approximately equal to n log n. So as you increase the number of elements in edge points, the computational time required to do this sort will increase in more than linearly, and that may be a disadvantage of using this technique. So it means if you do very small triangles, then this will be relatively fast. But as the triangles get larger, then this will introduce a relatively greater performance hit. There are, I suspect, other ways of doing it, probably using sort of clever things to detect precisely the particular geometry of the triangle that we're drawing, and then dealing with the edge points accordingly. The basic idea of interpolating between the vertices would remain the same. It is just a question of how precisely you go about ensuring that you can identify the pairs of x values that correspond to each y value. And as I say, you know, I've chosen to using sort, but I think there probably are computationally more efficient ways of doing it. For what I want to do, for what I want to use this library for, I think this is perfectly acceptable. We will have a look in a moment at what the sort of runtime is for this. And this is fast enough for what I want. If you're looking for some reason to create some kind of software equivalent of OpenGL or something like that, then you're going to want to look at much faster ways. I think much faster ways of doing this. I think this leads to really quite elegant code. I think this is a quite slick and elegant way actually of solving the problem, and I'm quite pleased with it. I'm just saying, I think perhaps there are other ways of doing it that might be more efficient. Anyway, I think what we should do is let's go to our terminal window. In fact, before we do that, let's just drop into capp.cpp. So, of course, capp.cpp is the main application class. We've talked about that before, does the actual implementation. So I've just modified this from the code that we had in the previous episode. And in the onInit function here, we actually establish all of our triangles. Now I've set this up to render a whole bunch of triangles of different shapes, different kind of dimensions, and also I've created 2 rectangular objects out of triangles so that we can have a look at how well they work for that. And I've set up a timer as well, so to time how long everything's going to take. So we're using a chrono from the chrono library in the standard library, and yeah, so we just record the time at the beginning, and then we record the time at the end, and then we can simply calculate using this functionality here how long in milliseconds everything took. Okay, and that's really it. So this implements a whole bunch of triangles. This is exactly the same syntax that we saw before in the previous episode. We simply add the different new instances of the triangle class into our object list vector, and that's everything. And then what I've done just down here in onLoop, I just commented out this code because we don't want to animate anything at the moment. So, and this also saves us the need to define a tvec list as well for all of these objects. We're not interested in that for the moment. That was just necessary for the previous episode to do animation. And on render, we haven't changed anything there, exactly the same as the previous episode. It just loops through every object in an object list and calls its render method accordingly. And that is all that we have to do. So we see we have a whole bunch of triangles here. In fact, 10 triangles are implemented. Let's go to our terminal window and let's compile our code. And let's have a look at how well that performs. Okay, if we clear that, let's run our code first. And there we go. We see here we have our 10 triangles. Okay, so these rectangular objects are both made of pairs of triangles. I was just testing that that worked, and I've implemented 10 triangles of various different geometries there, just to verify that the function, that the class works as it should for a variety of different cases. This may not actually be a completely exhaustive test of the algorithm. I believe that I have covered all the important possible geometrical variations, and I am quite confident the algorithm I have works in every case. Over the next week, as I come to use this code to go on to do other things, then if there are any limitations with the approach that I've done, they will become apparent, and I will talk about those then in the video next week. But I think we've covered it. I mean, if you, looking at my code, anyone watching this video identifies anything that I may have, any oversights that I may have made, please feel free to let me know in the comments below, and you know, I'll gladly take that on board in the next video. But I think I think the code I've written works. It makes triangles. We talked a bit about runtime. So we see there the runtime there is 20 milliseconds. Let's run that again a couple of times. There we get 18 milliseconds and 15 milliseconds. Let's do one more. And 15 milliseconds. Now, the important thing to remember is that I'm running my screen capture software on the same computer that I'm doing all this work on, which isn't particularly powerful to start with. So the screen capture software makes a significant hit on the performance. So 15 milliseconds to render 10 triangles, that's 1.5 milliseconds per triangle. That's quite slow. Without the screen capture software running, this comes in about 10 or maybe 12, between 10 and 12 milliseconds. You'll just have to take my word for that, but it does on my system. So we're looking somewhere about 1 to 1.2 milliseconds to draw a triangle. And these are triangles that, on average, for all of the triangles that we rendered here. They're different sizes, so of course the bigger ones will take a bit longer than the smaller ones, but we get an average of about 1 to 1.2 milliseconds per triangle, which is really not astonishingly fast by any means. It is, however, fast enough for what I want to do for my purposes, but as I have said already, I think there might be ways of doing it that don't involve using the sort function that might be a little bit quicker. But it really depends what you want to do, and I think the code I've come up with is quite elegant and nice, and as I say, it's fast enough for my purposes, so that's probably what I'm going to stick with. Okay, so that's actually everything for the code. Okay, so that's really everything I wanted to go over today. We've seen a basic approach for how to render filled triangles, which is a lot more efficient than using the FilledPoly code that we created a couple of episodes ago. And my intention really is to use this code for creating simple two-dimensional shapes and illustrations. So once we can do triangles, we can, of course, as we've seen, use those to create rectangles, and we can then render rectangles at any arbitrary rotation and things like that. And we can use it to generate a number of other actually quite complex shapes. So what I particularly, when I first started this series, really the functionality that I wanted was to be able to draw lines with SDL2 and to specify their thickness. Now that's a functionality that SDL2 does not support natively, so that's what prompted me to embark on this project of creating my own 2D primitives library, and hence this series. So over the next week, what I plan to do is to go on to actually implement those final shapes, so to implement classes to do rectangles and to do line segments. And we'll see if I go on to do anything else with that as well. But then that's pretty much broadly everything that I need. And then we'll go on to look at some things probably that will make use out of those new drawing capabilities that we now have. But we'll have to see how that goes. And I'm not going to say right now what those things might be, but I have some good ideas and I think some really quite exciting and interesting things coming up. So stay tuned for that. Okay, I mean, as I say, that's really everything that I wanted to talk about this week. I really hope you've enjoyed the video. It's been a great deal of pleasure making it. If you have enjoyed it, please remember to hit that like button, and if you haven't done so already, please remember to subscribe to my channel so you don't have to miss any future videos. Okay, well listen, it's really been a pleasure. I hope you found the video useful. Let me know in the comments below what you think. Let me know if you have any other particular ideas of content you'd like to see included in the 2D primitives library. That would be very interesting. If any of you suggest anything that I think sounds interesting, then I might go on to look at that. Otherwise, probably I think the next episode is going to be the last one in this particular series, and then we're going to move on to something else that will probably make use of the 2D primitives library that we have developed over the last few weeks. It really just leaves me to say, look, thank you very much for watching, and it's really been a pleasure, and I really look forward to seeing you in the next video. Bye.